In this video, we'll be discussing least squares classification. In a classification problem, the outcome or dependent variable y takes on only a finite number of values, and for this reason is sometimes called a label, or in statistics, categorical. In the simplest case, y only has two values. This is called the two-way classification problem, the binary classification problem, or the Boolean classification problem. We'll start by considering the Boolean classification problem. We will encode y as a real number, taking y equals positive 1 to mean true, and y equals negative 1 to mean false. As in real value data fitting, we assume that an approximate relationship of the form y approximately equals f of x holds, where the function f takes an n-vector argument and gives a resulting value that is either positive 1 or negative 1. Our model will have the form of y hat equals to f of hat of x, where the function f hat takes an n-vector argument and gives a resulting value that is either positive 1 or negative 1. Our model of f hat is called a classifier since it classifies n vectors into those for which f hat of x is equal to positive 1 and for those to which f hat of x equals negative 1. Some examples of Booleans used in real-life applications can be seen in email spam detection. The vector x in email spam detection contains features of an email message such as word count and number of capital letters. The outcome is positive 1 if the message is spam and negative 1 otherwise. The data used to create the classifier comes from users who have explicitly marked some messages as junk. Another example is disease detection. These examples correspond to patients with outcomes of y equals positive 1, meaning the patient has a particular disease, and y equals negative 1, meaning they do not. The vector x contains relevant medical features associated with the patient, including, for example, age, sex, results of the tests, and other features. The data used to build the model comes from hospital records or a medical study, and the outcome is the presence or absence of a disease confirmed by a doctor. Another example is Boolean document classification. The vector x in this case is word count or histogram vector for a document. The outcome y is positive if the document has some specific topic, for example, politics, negative 1 otherwise. The data is used to construct the classifier could come from a set of documents with their topics labeled. In regards to prediction errors in least squares classification, for a given data point xy with the predicted outcome of y hat equal to f hat of x, there's only 4 possibilities. A true positive, where y equals positive 1 and y hat equals positive 1, or true negative, y equals negative 1 and y hat equals negative 1, a false positive, y equals negative 1 and y hat equals positive 1, and false negative, y equals positive 1 and y hat equals negative 1. The first two cases, the predicted label is correct, and in the last two cases, the predicted label is an error. We refer to the third case as a false positive or type 1 error, and we refer to the fourth case as a false negative or type 2 error. This image right here shows a confusion matrix for the performance of a spam detector on a data set of 1,266 examples or emails, of which 127 are spam, meaning y equals positive 1, and the remaining 1,139 are not spam, y equals negative 1. In this data set, the classifier has 95 true positives, 1,120 true negatives, 19 false positives, and 32 false negatives. In regards to validation and classification problems, we're only concerned usually with error, true positive, and false positive rates. For the least squares classifier, we first carry out real valued least squares fitting of the outcome, ignoring for the moment that the outcome y takes on only the variables negative 1 and positive 1. We choose the basis functions f1 through fp, then choose the parameters theta 1 through theta p to minimize the sum squared error, as we can see here, where f tilde is equal to theta times f of theta 1 times f1 of x, all the way, adding all of them all the way to theta p times fp of x. The function f tilde is the least squares fit over our data set, and f tilde of x for a general vector x is a number. The final classifier is then taken to be f hat of x is equal to sine f hat of x, where sine a is equal to positive 1 when a is greater than or equal to 0, and sine a is equal to negative 1 when a is less than 0. The least squares classifier is often used with a regression model. For example, f tilde of x equals xt times beta, xt beta plus v, in which the classifier has a form of f hat of x is equal to sine xtb or xt beta plus v. In the iris flower classification, we illustrate the least squares classification with a famous data set, first used in the 1930s by statistician Ronald Fisher. These data are measurements of 4 attributes of 3 types of iris flowers: iris setosa, iris versicolor, and iris virginica. The data set contains 50 examples of each class. The 4 attributes are: x1 is the sepal length in centimeters, x2 is sepal width in centimeters, x3 is petal length in centimeters, and x4 is petal width in centimeters. We compute the Boolean classifier of the form and distinguish the class iris virginica from the other 2 classes. We use the entire set of 150 examples and find the coefficients given here. Here is the confusion matrix for the Boolean classifier of the iris dataset, similar to the SPAM confusion matrix that we saw before. Finally, to describe the code, we're first going to describe the description of the iris dataset. Just to recap, the data are measurements of 4 attributes of 3 types of iris flowers: iris setosa, iris versicolor, and iris virginica, as we can see here in the iris. And the data set will contain 50 examples of each class. And the 4 attributes are x1, x2, x3, and x4, which are contained here in this features matrix. And to train the classifier, we're going to have y return 1 if virginica and 0 if otherwise. And then we're going to create a matrix X that has a features matrix, regress X onto Y in order to obtain classification. And then finally, the difference between y hat and f tilde, the function f tilde, is the least squares fit, is f tilde is the least squares fit over our data set, while y hat is the predicted outcome, which is equal to sine of f tilde of x. The confusion matrix is finally made up of actual and predicted outcomes. And just a reminder, this is what it should look like before. Thank you.